Hello, this is Dr. Strickland. In this video, we will investigate the Henderson-Hasselbalch equation and talk about buffer capacity. Take a minute to read through these student learning objectives. These are the things you should be able to do by the end of this video so that you're ready for the more difficult things we will do together in class. The Henderson-Hasselbalch equation can be used to calculate the pH of a buffer solution or to determine the conjugate base to conjugate acid ratio needed when preparing a buffer solution. And the Henderson-Hasselbalch equation looks like this. pH is equal to the pKa of the conjugate acid plus the log of the concentration, the molarity of the conjugate base divided by the concentration of the conjugate acid. Now, sometimes we'll do this with concentrations, and sometimes we'll be able to simplify this to moles, but we'll talk about that. So, a few things I want to point out to you. This is the pH of the solution. And this is the pKa of the conjugate acid. So whatever it is. And so this could be a weak acid and its conjugate base, or it could be a weak base and its conjugate acid. And so I wrote them like this just so that regardless of which partner was charged and which was uncharged, it would still be the conjugate base over the conjugate acid. All right, so let's look at some practice problems. And I wanted to remind you, strategy that we used in Chapter 8 is also useful here with nomenclature, classification, and then calculation. Because you have to confirm that you have a buffer before you can use the Henderson-Hasselbalch equation to calculate its pH. So if you've got words here, then it'd be a good idea to put their structures on them. So ammonia is NH3, and ammonium chloride is NH4Cl, and we're just going to start with the simple ones. There are much larger ones that we'll see as we go along. So we know that we've got a conjugate base and its conjugate acid tied up in a soluble salt. So we're good to go. Weak acid, soluble salt, meaning 4+. This is the weak base component. Weak acid. Okay, so we've confirmed that we've got our weak acid, weak base pair. We can look up the pKa of the conjugate acid. So pKa of the ammonium ion, you can look up in the table that's in the appendix, and that's 9.245. Okay, so in this case, what we want to know is the pH. So we've got 9.5 plus the conjugate base over the conjugate acid. Now, the reason I like to label them is because that helps me remember which was which. So the ammonia is the conjugate base. So the 0.200 more goes on the top. And then here, 5 molar of ammonium chloride with 100% ionization, 1-to-1 molar ratio. That means that we've got a 0.500 molar concentration of the ammonium ion also. And I'm going to put the units in here right now, but you see they cancel. And as long as you know that they're both molar, then you really don't even have to show them. All right, so I want you to do the math and then tell me what the pH is, and then come on back. All right, welcome back. and I got 8.847. Did you get it? All right. So as you use the appendix in the back, remember that the name always goes with the uncharged form, whichever it is, and pKa always goes with the conjugate acid form. All right, so come on down here. Sodium hypochlorite, NaOCl, which is the active ingredient in chlorine bleach, was dissolved in a solution buffered pH 6.20. Find the ratio of the conjugate base to the conjugate acid concentrations. So let's see what we got here. All right, so this is a weak acid. This is hypochlorous acid. So it's a good idea to know the names because they're going to be listed by the names in the appendix. And this is the hypochlorite ion. And if it's been a while since you've done the names of the oxyacids and their anions, that would be a really good thing to check out. Okay, so weak acid, weak base. Okay, so pH related to pKa, it's all Henderson-Hasselbalch. Probably be a good idea to go ahead and look up the pKa of this guy. And when I looked it up, I found 7.53. All right, so this is our basic format. What we're looking for is this ratio this time. We know the pH of the solution, we know the pKa of the conjugate acid. So let's see, 6.20 is equal to 7.53 plus the log of this over that. Conjugate base over the conjugate acid. All right, so what I want you to do is solve for this ratio. Pause the video, solve for that ratio, and come on back. All right, welcome back. So, bet you got this. 0.0467. Yes. All right. So let's come on down here to buffer capacity. Buffer capacity measures how well a buffer resists changes to pH when strong acid or strong base is added. It's measured as the number of moles of strong acid or strong base that causes 1 liter of a buffer undergo a 1.00 unit change in pH. So the big job of a buffer is to keep the pH of the surroundings stable. It happens in our bloodstream all the time. You know, we have to have pH in our blood between 7.35 and 7.45, which is not a very big range. And it, you know, so our blood has to defend that pH against any strong acid or strong base that might come into our bodies from a variety of sources. So buffers are very important solutions. And so buffer capacity means, you know, how well can a buffer do its job? So the greater the buffer capacity, the smaller the pH change when the buffer encounters a small amount of these guys. And buffer capacity is also at a maximum when the pH of the solution equals the pKa of the conjugate acid from the buffer. So if we know we need a buffer of a particular pH, first thing we're going to do is go to the appendix and look for a weak acid that has a pKa that's somewhere close to that. All right, so let's look down here and see which one of these guys might be best if we wanted to prepare a buffer that had a pH of 3.10. Okay, so if I look up the pKa's of these, hydroxybenzene, which is also called a phenol, has a pKa of 9.997. Phenoic acid has a pKa of 4.874. All right, so I want you to go find the appendix and find the pKas of these two guys, and then come on back. All right, welcome back. So cyanoacetic acid, I got 2.472. And sulfuric acid, I got 1.987. And if you went, wait, sulfuric acid is a strong acid. That can't be what we use. That's correct. We're looking for a weak acid. And you know the sulfuric acid is on the strong acid list. So it's got to be one of these three. And so the one that's the closest, I think, this one is high by 1.8-ish, and this one is low by less than 1. So we're going to go with this one. This would be the best acid to use because it has a pKa that's the closest to the desired pH. It doesn't matter if it's above or below. All right. And one other thing about buffer capacity is that it increases as the concentration of the buffer increases. And the reason that happens is because there are more molecules. There are more conjugate acid. Well, here, the weak acid. Let's just put that in parentheses. There are more weak acid molecules to neutralize incoming strong acid. And also, on the flip side, there are more conjugate base molecules to neutralize incoming. I did this backwards. All right, let me write it down and we'll walk back through it. There are more conjugate acid molecules to neutralize incoming strong base. That's not even very visible. Just try that again. There we go. And there are more conjugate base molecules to neutralize incoming strong acid. All right, so that is the basic story on the Henderson-Hasselbalch equation and buffer capacity. If you have any questions, send them to me.